So she's from the States, Emily. She did the undergraduate student at Johns Hopkins University, and then she moved to Australia, where she did the PhD. It was in Melbourne, in Swinburne University of Technology, and then after there, she also became involved in a big team, the Wisnioski Dark Energy Survey. You are still a member of this collaboration, which is somehow a different topic, but you are very much involved in that. And then she moved with a postdoc to Germany, to the Max Planck Institute. She is now part of the big group that we all know, Genzel's group, studying the properties of star formation, galaxies, and at higher redshift. The reason why she's here is first because we were aware, when I say we, I mean our collaboration estallido. She has been invited by us. So we were aware, we were using her papers, which are related to some of the topics we are doing here. She's also very nice, and if you read her paper, there are a lot of references, not only to us, but also to more people at this institute. And also, we contacted her thanks to Javier Rodriguez-Saurin, that in one of the meetings, she happened to meet her, and then he knew that she was moving to Europe, and then we thought it was an excellent opportunity to invite her to visit us while he was nearer than Australia, so in Europe. And so we did, and she nicely accepted our invitation. So this is the first time for her here, the first time in the Canarias, the first time at the ISC, the first time with us. And just to tell you that we have been with her already yesterday. She's very nice. She already has a lot of things that interest to us. We hope to be able to start a collaboration in the future, and maybe not only with us, but with many of you who are now listening. So that's all for you. So take your time, and we are sure we are going to enjoy your talk and the things you are going to tell us.
Thank you. I hope you. So star formation both locally and in high redshift galaxies. And by high redshift, I mean redshift about 1 or 2. This is work that I've primarily done for my thesis in Australia with both the Wiggles and the Dynamo team. So the sort of big question that's motivating this research is, how do galaxies form? And so here I've just shown some pictorial representations of the different models in the literature. So here on the left, we have just a galaxy forming in isolation, where you have gas and it's expelled over time through star formation, and the galaxy evolves to be sort of an older galaxy. Here we have the more violent formation mechanism of galaxies merging, which can cause new star formation, but also can quench star formation in galaxies. And then here in the larger picture is this more recent theory where high redshift galaxies are fed pristine gas from the intergalactic medium and the cosmological flows. And so the gas falls onto the galaxy, causing more star formation events to occur. Okay, this is a big question, and I don't hope to solve it with just this talk, but if we can break it down into some more bite-sized questions. Where do the galaxies get their gas? And where does star formation occur within the galaxies, particularly at high redshift? And are these formation mechanisms different at high redshift than at low redshift? And what's motivating this last question is the star formation rate density of the universe. So here you have the star formation rate per unit volume versus cosmic time. And we know that at redshifts of 2 and 3, there's far more star formation per unit volume in the universe than there is today. And so we want to know what effect, if any, this has on galaxy evolution and star formation within star-forming galaxies. And so for my talk, I'll actually be talking more about the star-forming regions within galaxies rather than galaxies themselves. And so this sort of raises more questions of how do star-forming regions form within star-forming galaxies? Is it the same at different epochs? And how much do the galaxy properties affect the star-forming properties of the regions that are forming in them? Okay, so this is sort of the picture that we have at low redshift of blue star-forming galaxies. They're typically spiral galaxies, like you can see here. These are from the SINGS survey. They're NGC galaxies. And these star-forming spirals typically have about hundreds to thousands of star-forming, or H2 regions within them. And these H2 regions are typically tens to hundreds of kiloparsecs. But when we go to high redshift, the blue population looks a little bit different. So these are galaxies from the Hubble Deep Field at redshifts of 1 and 2. And you can see that the star-forming regions within these galaxies are quite large compared to the overall galaxy. There's only a handful in each galaxy. And they're sort of distributed throughout at random. So these are more what we'd call irregular galaxies in the local universe. And when we do some more studies on these high redshift galaxies, we'd say, well, they actually look more like local dwarf galaxies. So here you have, in this column, an image of a local galaxy. And then these papers that artificially redshifted them are basically blurred them to the resolution of high redshift surveys. And you can see what they would maybe look like if they were put at high redshift and compare them to what we actually observe at high redshift. And you can see that sort of local dwarf irregulars are what seem to match morphologically what we see at high redshift, whereas these more constant surface luminosity spiral galaxies, you don't see these really strong clumps in them. And so when you look at these images statistically, you find that the blue population or star-forming population at high redshift, the majority of these galaxies have irregular morphologies, whereas locally it's only a small fraction. And the clumps within the high redshift galaxies are very large, and they typically have much higher surface densities than the disk that they're found in. Okay, so another way of trying to look at these morphologies is to just simply measure the star formation and size of regions or star-forming regions in local galaxies and at high redshift. So here the black points here are from H2 regions in local galaxies. And the red points are from these clumpy galaxies found at high redshift. And what was found in this study by Mark Swinbank and Tucker Jones is that there's a 2 order of magnitude offset in star formation at a given size for star-forming regions locally than at high redshift. And so this was sort of puzzling. What's causing this difference here? And so the first stabs at trying to explain this was, well, maybe there's a higher efficiency at high redshift. These galaxies are forming their stars more quickly, so maybe what we're seeing are starbursts rather than H2 regions. Maybe these aren't really comparable. But it could also be that the galaxies at high redshift are more primordial. Maybe they have lower metallicity, and this could be affecting this offset here. This is something we want to understand better, and right now we only have about 10 points that are constraining this difference. But before we can really start probing that diagram, we need to understand, are we really comparing the same thing? Are these clumpy galaxies at high redshift actually disks? And so this is some work done by Reinhard Genzel's group in the Msun survey, where they've taken an IFU and looked at some of the clumpy galaxies. So here you see 2 examples of the H-alpha morphology of these redshift 2 galaxies. And the scale bar here shows 5 kiloparsecs. And so there's a couple clumps in them, you can see here. And we want to know, do these last? Is this just instantaneous star formation? And here is a rest frame optical image of these galaxies, where you might imagine there's a bit of an older stellar population. And you can see there's still clumps in these galaxies. They still have irregular morphologies. You might even say, you know, they're different. The clumps are different. Here in the H-alpha, you don't see anything under this clump A, whereas in the older stellar population, you do see some clumps. So it seems like some of them can be involving later into these galaxies' lifetimes. And are they disks? Well, these 2 are. You can see here their velocity gradients is from IFU data from Symphony on the VLT. So it seems like these clumpy galaxies are actually disks. And when you go into the literature and look at all the high redshift IFU surveys, and you find the galaxies that have a clumpy H-alpha morphology, the majority of them seem to have disk-like rotation. So this is the Msun survey. It's the state-of-the-art sort of redshift 2 IFU survey, which is looking at probing the kinematics of galaxies. And they have a wide range. These are all the velocity maps from the galaxies. And when you break it down, they have about 10 or so disks. And so we can start to constrain this sort of star formation within high redshift galaxies using this data. But 10 galaxies isn't so much. Here's another IFU sample that I published a couple of years ago for my thesis, where we studied 13 galaxies. And I'll go into this in a little bit more detail later, but what I want to point out here is that we found also some clumpy galaxies at high redshift. And we think if we add these with some of the other galaxies from the literature, we can start studying star-forming regions at high redshift. But when you put it all together, and here's just a laundry list of all the IFU surveys at high redshift from different telescopes, Symphony at the VLT, NIFS on Gemini, the OSIRIS Integral Field Unit on Keck. There's about 200 galaxies at redshifts greater than 1 that have been studied with IFUs. So we're starting to get good numbers here, but I mean, it's across many different papers, different groups. Things have been selected in different ways. We have lens galaxies, non-lens galaxies. And to really study star formation at high redshift, we want to just look at disk galaxies where we've resolved star-forming regions. So when we cut that down, there's about 15 galaxies at redshift 1 that have clumpy morphologies where we can really get at the clumps using AO, or adaptive optics, to get a better resolution. So there's not too many at the moment to look at, but there's still some hope to try to measure the star formation in them. But before we do that, we want to understand, okay, we have these two different epochs, and what's different about them? What could be affecting the galaxies and the star formation within them? So just to sort of connect the two regimes, I'm first going to talk about how star formation changes from higher redshift to today. As we saw in the star formation rate surface density diagram, at high redshift there's more star formation per unit volume. But here we look at star formation versus stellar mass, and we can sort of see the same thing, where this is from the Deep 2 survey, and here in 4 different redshift bins. If you look at the blue star-forming population, they seem to form this consistent relationship across all epochs. And this is sort of called the main sequence of star formation. And what you can also see, not only does it exist at all redshifts, but it seems to evolve. So at higher redshift, the normalization is higher. So all of these star-forming galaxies are forming stars at a higher rate. So this sort of is the evolution with the star formation rate density. So there's more star formation at high redshift, but what about gas? And so here we have a diagram of this is molecular gas fraction versus redshift. You may not be able to read the numbers, but what you can take away is that at redshift 2, galaxies typically have 50% of molecular gas as their total mass, versus locally where we find that galaxies have about 10% gas fraction. So there's much more molecular gas in these galaxies at high redshift for stars to form. And maybe this is what's causing these higher star formation rates. And in fact, there's a recent result from Linda Tacconi. Again, here we have molecular gas fraction. This is versus specific star formation rate, which is the star formation rate per stellar mass, is that it seems to correlate, the gas fraction seems to correlate well with star formation. So the more gas you have, the higher star formation rates you're getting per unit mass. So this seems to all fit in with each other. There's more gas at high redshift, more star formation. But are things really that different? So here again we have the star formation main sequence of star formation versus stellar mass. And we're in 3 different redshift bins from today out to redshift 2. But now the galaxies are color-coded by their Sirsic index, so it's sort of a measure of their underlying structure, where black and blue represents more disk-like systems with a Sirsic index of about 1, whereas this sort of red cloud down here represents galaxies that have a Sirsic index around 4, so more passively evolving galaxies. And you can see there's a clear separation locally, where this main sequence is made up of star-forming disk galaxies. But this seems to hold all the way out to redshift 2. So even though the star-forming galaxies do look different, their underlying sort of structure is still disk-like. And so, yes, they have higher star formation rates. Yes, there's more gas, but the sort of same statistical parameters are seen both at high redshift and low redshift. Okay, so the last thing I want to talk about to bring the two epochs together is gas turbulence, or sort of the velocity dispersion of the gas in galaxies. So we see locally the velocity dispersion measured in kilometers per second versus sort of the star formation rate density. You typically get velocity dispersions around 10 to 20 kilometers per second in local NGC disk galaxies. But when you go out to higher redshift, and there's this correlation between star formation and velocity dispersion. When you go out to higher redshift, this correlation seems to continue, where at higher and higher star formation rates or luminosities, you also get higher velocity dispersions. So in high redshift disks, shown here by the colored blue, purple, and pink points, you see disk dispersions of about 60 to 100 kilometers per second. And this has been found in most high redshift IFU surveys, that disks and all galaxies in general have very high local velocity dispersions. Okay, so there's more gas at high redshift, more star formation. Seems like the gas in the galaxies is more turbulent. So what are we really asking? What's different at high redshift, and are all the mechanisms maybe the same, but the environment is different, and how can this change the star formation that goes on within galaxies? So theoretically, people have tried to explain this by modeling how these disk galaxies could form. So here's an example of one of the models from Elma Green et al. And there's many other examples. But the general picture is you have an unstable, turbulent disk at high redshift. And within this disk, star-forming regions form out of gravitational instabilities. And then over about a giga-year or less, these star-forming regions can merge with each other, and they, through dynamical friction, collapse towards the center, and they form a pseudo-bulge. So this is one picture. There's other evolutionary tracks for the star-forming regions, but what you should take away from these models is that they typically aim to have star-forming regions form that are about a kiloparsec in size and 10 to the 8 to 10 to the 9 in stellar mass. And to do this, they usually need to have some sort of cosmological context to increase the turbulence, which in the models causes the star-forming regions to form. So one of the ways to do this is to have this cold, pristine gas falling into high redshift galaxies. And this is a way to increase the turbulence in the galaxies to make them unstable. But once the star-forming regions form, the galaxy could become less turbulent. But that's not what we observe. So in the models, they need a way to continually add turbulence and instability into the disk. So there's differences in the model as to how this is done. One way is just to continuously add more and more gas to the galaxy by having more accretion. Another way is to look at the feedback from star-forming events and other motions in the galaxy. This can also act to drive up the turbulence. There's also star formation, which has been suggested, and as well clump rotation. So if these clumps are living long enough, they're very massive, they can have a high velocity dispersion as well. But despite these differences, they're all there to help inject turbulence and instability in the models. One of the main differences that the models do have, though, is what happens to the clumps that are forming within the disks. This is the fate of the clumps. So if feedback is in fact important, if the clumps themselves are hosting winds, then they would form, and as they're forming stars, they're blowing out some of their gas. And eventually they could blow themselves out if their winds are stronger than their star formation rates. And this could happen within less than a giga-year. And if there aren't winds, then you'd get some more classical picture, which I showed before, where clumps form, they evolve within the disk, maybe mix with some other clumps, and then coalesce to the center as they grow. And so another way to look at these differences is to look at the mass versus time in these simulations. So if you don't have any winds in the simulation, you get this black line for a clump mass. It will just continue to grow over a few hundred megayears. But if you do have winds in these simulations, you get these colored lines where within 50 megayears, your clumps can form and then be dissipated. And so in these simulations, it's really important how this turbulence continues to function in the galaxy, because you have to have many different episodes of clump formation to get the observations that we see today. Okay, so coming back to the data and this diagram again of star formation versus size, we want to understand there clearly is some empirical relation here between these parameters, and we want to know what's going on here. There's more star formation, more gas, but is that really a reason for this offset here? But before we do this, well, we want to understand what's been done at low redshift to understand this relation. And there's obviously been a lot of research done on H2 regions, and a lot of it done here. And H2 regions do seem to form this relationship between luminosity and size. But there are also very turbulent H2 regions, giant H2 regions, which have supersonic velocities. These are capable of hosting winds, just as the high redshift galaxy clumps are. So they do seem to be comparable objects that we want to explore further. And when you add this third dimension using the velocity dispersion of regions measured from the line width of, say, H alpha, you see that there's sort of scaling relations for these local H2 regions, where here you have size versus velocity dispersion, luminosity versus velocity dispersion. There's many examples in the literature. But there doesn't seem, as far as I could tell, much agreement between what the actual relations are. And here's just sort of a list, shows the range of what's been fit to the data throughout different papers. You can see exponents ranging from 1 to 4 or 3 to 6. So there's quite a range in what people find locally. There's also quite a range in the explanations for these correlations seen at low redshift. And I won't go through the list, but there's many different physical scenarios that could explain the different relationships. Okay, so to bring this back to connecting the low redshift and the high redshift data, we clearly need more points to test if these are right. And to do this, we need very good resolution. And from the ground, that means using adaptive optics. So we need some AO observations or maybe some Hubble observations. But we want to fold in this third parameter of velocity dispersion. So we're not just looking at one scaling relation, but possibly 3 scaling relations. So to do that, we need integral field data. So we need some integral field AO observations. And also, we maybe want to incorporate some more of the literature since there's such a wealth of data there. Okay, so this brings me back to the sample that I published in my thesis. So what we did is we studied 13 star-forming galaxies. They were selected for having a high luminosity. And we observed them with the OSIRIS instrument on Keck, so not here, but over in Hawaii. And it's a infrared IFU. Its spatial resolution is 50 milliarcseconds, and it has a spectral resolution of 3,500. So here I've just shown the H alpha images of these galaxies. So I've collapsed the cube to just see what the H alpha would look like. And you can see we have a range of morphologies, but I'll focus mostly just on these clumpy galaxies here. And if you are familiar with some of the other high redshift IFU surveys, here's just luminosity versus redshift. And these galaxies, which I'm talking about, are shown here in red. So there's some of the most luminous galaxies studied at this redshift with IFUs. Some work done with the VVDS survey, shown here. Work done by Shelley Wright, also with OSIRIS, David Law, and the Msun survey, which spans this whole redshift range from about redshift of 1.5 to 2.5. So what we want to do is measure these star-forming regions in the clumpy galaxies and compare them to local H2 region properties. So we find 8 regions within the Wiggles galaxies. So here's this diagram again. Now I'm going to plot the Wiggles points on it. So here is now the same diagram plotted as H alpha luminosity versus diameter. And these blue points here are the red points in the previous diagram, and they're taken from redshift 2 lens galaxies. And these are measured H2 regions from SING's local H2 regions. Okay, so when I add in some more data, here are the Wiggles clumps that you just saw in red, and some more high redshift clumps from the Msun survey shown by the blue triangles. And I've also taken in some giant H2 region data from the literature, which seems to fill in this gap between the low redshift and high redshift data. So these open black symbols are giant H2 regions observed locally. And what I see from this diagram is that we don't recover in Wiggles the same 2 order of magnitude offset in star formation. It seems like there's more of a continuum here, that these high redshift points, while they're still a bit offset here, they're not as offset as the other points. And they seem to follow pretty well with the local data. And you should also note that there's maybe an observational bias here where we just can't observe these very large regions that have low H alpha luminosity with the current data set. Okay, so when we can add in, just to make this point, we're not just looking at star-forming regions within spiral normal galaxies. This difference is not because we're looking at different types of galaxies. So locally, we're taking these giant H2 regions and normal H2 regions from spiral galaxies, but also irregular galaxies, dwarf irregulars, and even ULIRCs. They all seem to fall generally on the same line. And at high redshift, the star-forming regions or clumps are taken from both sort of main sequence or normal star-forming galaxies, as well as L-star or sub-L star galaxies. So we're probing a range of different environments. Okay, but when we add in the information we get from IFUs or in the literature from Fabre-Priot data, we get these three scaling relations, where here now we have velocity dispersion versus size, H-alpha luminosity versus velocity dispersion in the same luminosity versus size here. And here you have the giant H2 regions, again, the open symbols in black, and the clumps here shown in color. And what we see is that in all of these correlations, the high redshift data seems to just extend the low redshift data. It's not perfect. There's still some offsets here, but it doesn't seem as different as was initially suggested from the data. Okay, so I'm going to go through each of these and try to explain. There's clearly some empirical relation here, but is there a theoretical basis that we can use to explain what's going on? So the first is, again, this luminosity versus size that we keep coming back to. And one of the most typical theoretical explanations for this relation is to use a strong-room sphere argument, where an H2 region is formed from a strong-room sphere. And if this is true, then you'd expect the luminosity of the region to go as something like r cubed, or the size cubed. And we find an exponent of more like 2.7 empirically. So this is a bit shallower than the strong-room sphere, what you'd expect. But, it's not, the data isn't perfect. There's different biases. Maybe some of the more luminous regions have escaping photons, which could cause the shallower slope. Could also be resolution and dust effects. But this is sort of one possible explanation for what could be driving this relation here. In terms of the size and velocity dispersion, you can see that this relation has maybe a bit more scatter. But from the models of high redshift galaxy evolution, we might say that this is something to do with genes collapse in unstable, tumorally unstable disks. So if this were true, the gene's length would go as sigma squared. And when we fit a relation to this, we get something pretty close to that. It's not perfect. These points the Wiggles points seem to fall a bit above the fitted relation. And this could be due to an observational bias where in high redshift it's really difficult to take out the overall disk dispersion contribution. So you measure the dispersion of the overall disk, but to actually get the dispersion of the clump can be quite difficult. So that could be one thing biasing these points. So if you fit this relation to the data, you can also get out sort of a surface density of the disk. And if we do that, we get a surface density of about 500 to 3,000 solar masses per parsec squared, which is not out of line with the models. So it's not a perfect explanation, but it seems to do all right here. And if we try to take this one step further and see if we can use this gene's argument to explain the luminosity versus velocity dispersion, we're here at the low redshift points and the high redshift points. You could say that we expect the gene's mass to go as sigma to the fourth. And when we fit a relationship here, we get an exponent of 4.2. So it's pretty close. But for this to hold, you would have to assume that mass is proportional to light, or mass follows light. And we can't really say definitively that that's true. We try to get at that a little bit more, where now we plot the luminosity versus a sort of derived mass for these regions, where the mass goes as sigma squared times r. And so this follows from either a dynamical mass argument or a gene's mass argument. And you can see this tightens up the relationship quite a bit, where the blue line here is fitted to the data. But this black dashed line shows mass proportional to light. So, it's not exactly following. So there's some deviations here. These aren't perfect explanations, but they don't seem so outrageous or so wrong from the models. And so if we try to look a little bit more at the mass of these regions, so there's this relationship holds for both virial mass or dynamical mass but also for a gene's mass, where the only difference is sort of the the constants that go in here. And so if we calculate a virial mass, we find that the clumps are 50 to 90% of the total stellar disk, which we get from an SED fit. And so this seems a bit high. It means that the disk is only 10% of the total mass of the galaxies, and these clumps are really creating the most of the mass. Whereas if we use a gene's mass, we get more that the clumps are about 20 to 30% of the overall stellar disk. And this is more in line with the models. So again, the gene's scenario seems to fit better here. Okay, so those are the sort of scaling relations that we can look at, and it doesn't seem like the high redshift and the low redshift are so different, or at least not as different as was first proposed. But what can we also try to get at this question of the turbulence in these disks? What's causing these high dispersion values within the disks and within the clumps? Can we try to constrain if it's one of these four things or a mixture of the two? So one way to look at this is to look at the surface density versus velocity dispersion. So it's been proposed that this is just a consequence of two-ray unstable disks plus the Kennekitt-Schmidt law, where if you have an unstable disk, the two-ray parameter is 1 or less than 1. So here you just have 1, and then you put in the Kennekitt-Schmidt law. And then you get this relationship here, where sigma is proportional to the star formation surface density to some power. But it's also been proposed that this is mechanical energy from star formation that's driving this relationship. And that would give you this equation here. So if we try to constrain that with the models, see, it's pretty noisy. Definitely need better data and more of it, just like all of astronomy. And unfortunately, what we get is this very tantalizing 0.6 plus or minus 1, which is consistent with both. So we can't yet say anything, but you can see how, if the data were a bit better, you could start constraining this. And personally, I would say that this top explanation seems a bit more reasonable and is more in line with the relationships I've been discussing so far. So what about clump rotations? So if these clumps evolve long enough, they would become virialized, and they would have their own rotation, which you could detect the signature of and maybe better understand what the objects themselves are. Unfortunately, we also cannot constrain this model. So here's an example from one of the simulations, where here you have H-alpha luminosity of clumps, where the disk has been subtracted, their velocity and their velocity dispersion. And this is sort of the typical resolution of current data. So you can see, while taking in the PSF and whatnot, you can get back the actual size of these regions, but it's quite difficult to get at their actual velocity gradient or dispersion. There's just too much blurring here. We need better data, so we can't really constrain this question. But just to conclude about these scaling relations, it seems like, in my opinion, the star-forming regions at high redshift are similar to star-forming regions at low redshift. They're bigger, they're forming stars more quickly, or they have higher star formation rates. But they seem like they follow similar relations. They maybe are at least comparable to each other. And we put forth this genes or tumor instability model to help explain what's driving these correlations. But there's a lot of things that can affect these observed scaling relations, such as measurement errors, which I've suggested. It's hard to get at the actual dispersion. There's, of course, always resolution effects. Some of the scatter could be real, such as variations in the star formation surface density due to the Kennekitt-Schmidt law. And there's contribution from winds. If these clumps are hosting winds, as we know some local H2 regions do, this can bias the velocity dispersion that we're measuring. Okay. There's been some work since I published these scaling relations from Livermore et al. And Swinbank et al. And they've used some high redshift Hubble imaging. But overall, the agreement in the literature is that this genes argument provides a reasonable explanation for what's being seen. And there's some differences in the interpretation of, is this a higher dispersion because of higher dispersions in the galaxy, higher gas fractions? But it's kind of hard at this point to unlink what is actually the cause of these larger regions. Okay, but can we actually get at any of these questions? How about whether or not they host these large stellar winds? Can we detect that at high redshift? So a signature of this might be broad and observed line widths, where you're seeing some signature of the wind underneath the narrow emission line that we observe. This could also increase the turbulence in the disk around the clumps. If we could get at the age, that might help us understand if these clumps have survived a long period of time or are quite young. And maybe even just whether or not we see them in the central regions of galaxies, or if they're all at the outer edges. Okay, so here I've gone and stacked the H-alpha emission line from the 8 clumps that we observe in Wiggles. So here's just the H-alpha. And what we've done is we've fit both a broad component and a narrow component. And the broad component is signifying the wind in the galaxy. We find that it's very statistically significant to have the 2 components. And in the broad component, we find a full width half max of about 500 kilometers per second. So this is consistent with hosting a large wind. It's also blue shifted about 25 kilometers per second from the narrow emission line fit. And so we can only see this in the stack, but it does seem to indicate that some of the clumps are hosting winds. It also gives us an indication that in individual clump H-alpha, we're getting contamination from the winds probably. So our velocity dispersions might be a little bit higher because we're not detecting this broad wind underneath them. And this has also been seen in the work by the Msun survey by Genzel and his student Sarah Newman, where they get a similarly large, about 500 to 1,000 kilometer per second broad component from a stellar wind. So does this actually indicate these clumps are blowing themselves out and being destroyed, not actually coalescing to the center and forming a bulge? Well, it may be more complicated. Yes, we see blue shifted broad emission, which is indication of winds, which supports this blowout theory where the clumps are expelling winds and blowing themselves out. In the Msun survey, they measure a mass outflow rate of the clumps, and they find that it's 1 to 8 times the star formation in the galaxy, in the clump itself, which indicates that it's expelling far more gas than it is forming stars. So this is a strong indication that some of the clumps are blowing themselves out. But we find clumps towards the center of the galaxy, which indicates that they are migrating. And in HST data, there's also been found clump age gradients in the disk, showing that some of the clumps are evolving. So there's sort of evidence for both models, and I would say that it's more complicated, of course, and maybe some of the clumps are forming stars so greatly that they are blowing themselves out, whereas others are able to migrate to the center. I mean, both scenarios seem equally likely and could probably both happen simultaneously. Okay, so just to summarize a little, are these clumps giant H2 regions? Well, they're where the star formation is occurring in galaxies, and some seem to survive long enough from we see from the broadband imaging to contain older stars. They host stellar winds just like low redshift H2 regions, and they seem to follow the same or similar scaling relations. So I think this is pretty good evidence that these are comparable objects. Can we constrain what drives the turbulence in the galaxy that's making them unstable? Where these are, could be gas accretion, gravitational motions of the clumps, stellar feedback, or star formation. I would say we can't constrain this. It probably is a combination of many of these things. But what happens at the end? Well, we have some observational ways of probing this. Are they coalescing to form a bulge? Or are they disrupted? And I think this is both. Both of these things should happen. It seems reasonable. Okay, so this is sort of the current state of these 8 comparisons between H2 regions and giant clumps. So what can we do next? So just before I finish, I'm going to briefly go over a new survey that we're working on called the Dynamo survey. And so this is a survey of about 100 galaxies selected from Sloan at redshift about 0.1 to 0.2. And we've looked at them with a 4-meter telescope in Australia to get their H-alpha kinematics. So here are some of the velocity maps from H-alpha. And they have a comparable resolution to the high redshift seen limited studies. This is a good comparison sample to high redshift galaxies. And one of the main discoveries in this sample is that these galaxies have very high local velocity dispersions, but they're local galaxies, so they have velocity dispersions about 40 kilometers per second. So these are quite rare, we think, that we found locally. And so a project within this survey that I'm working on is we got high-resolution IFU data for about 20 galaxies in the sample. And we picked galaxies that we knew were disks, and they had high velocity dispersions. So the reason why we're following them up with higher resolution IFU data is because we thought, okay, at high redshift, the high velocity dispersion objects have this clumpy morphology. So here we have locally high dispersion disk galaxies. Maybe they also have clumpy star formation. And we found, in fact, that they do. We see more ordered star formation than at high redshift, where you have rings, but also we see some spiral arms. So this is Passion Alpha images of these galaxies taken again with the OSIRIS IFU on Keck. So we're using here Passion Alpha as a proxy for H-alpha. And here's an example of 6 of the Passion Alpha images. So these look similar to these high redshift clumpy galaxies. Can we use this data to further constrain, to get to a better spatial resolution, to fill in some more of these scaling relations? And there's a lot of advantages to going to the lower redshift. You can get far more information than in high redshift. So here's again, in green, the Passion Alpha emission from the galaxies. But I've also included now a continuum, which we also get from the IFU data in red. So one of the big advantages of having this continuum emission that you don't get it typically at high redshift is you get a much better constraint on where the center of the kinematics in the galaxy is, or just where the center of mass in the galaxy is. You can see here you might get it wrong, but with the continuum you get a better idea. And this can help us just figure out which are central clumps, which aren't, and various other things. And so this has been done to some extent at high redshift, so this is from the Msun survey. But the resolution that we're getting is far better. So, a clump here is typically 500 parsecs, whereas the clumps here are over a kiloparsec. So we think that we can really start to improve this analysis by moving to the low redshift. And just, again, some examples of how we can do that is we can get a better constraint on the distance the clump is away from the center of the disk, can measure their dispersion sizes, as I've said. And so this is work that we're doing now and hopefully we'll publish in the coming year. So, thank you.
Thank you very much, Emily. So we have 15 minutes for questions.
Yeah, you mentioned at the beginning the possible role of the metallicity. So after this, can you say anything about it?
Metallicity can be quite difficult at high redshift. Typically, it's gotten from an N2 to H-alpha ratio to get sort of the oxygen abundance. But within the clumps, the signal to noise you can get typically a metallicity for a galaxy, but for a clump, you don't get the N2 strong enough to measure a good metallicity. So I think that's something for higher signal to noise data in the future.
Okay, I have two short questions. The first one is again about metallicity and whether the scaling relationship that you have several of them, they do depend on metallicity. This has been studied, and does the metallicity explain the large scatter observed at high redshift?
Similar answer. It's hard to get at a metallicity, and the high redshift data doesn't span a very large
but probably
dynamic range.
This can be done at low
redshift, yes. There
so
have been studies. I think there is some correlation, but it's not a very strong one. But I could be maybe should be
Okay.
corrected.
And could you mention the masses, the typical masses of the galaxies in the dynamo sample, the last one that you...
Yes, they typically lie along the Sloan main sequence, so a 10 to the 10, but they span
So
quite
they are
a
not
wide
dwarfs.
range.
They are not dwarfs.
They're not dwarfs, no.
Okay.
So most of your inference about evolution in the clamps and so on are coming from the plot that you're showing star formation rates versus sizes. But you haven't said very little on the difficulties observing at high redshift in terms of the size that you're able to measure and also the luminosity cut. No? So it would be nice to, if you go back to this plot and tell us whether are those limits. And also I have a question related to the technical details about how you measure a diameter in a clamp, or how do you define the size of the clamp because you have the clamps embedded in a disk, no?
Yes.
So it's related to some kind of contrast between the, it's not clear to me how you do that.
Yes, no, that's a good question. The observational biases are there, and it's hard to say exactly what effect they'd have. I mean, we can only observe the brightest things, and we do see offsets from the local relationship, so this could explain it. But some of the points are from lens galaxies, which are L-star, sub-L-star galaxies, so we also have some range there. But I suspect this will play a role.
But if you were not measuring clamp, but just simply the surface brightness of the disk, you would see the gap too, because of the different star formation rate in general of the galaxies. So I want to understand, how do you define a clamp really? How do you measure? What is the contrast value? How do you measure the sizes? So
for clump sizes, we spent a lot of time thinking about this. There's two ways that are typically used in the literature to measure a clump. The first is an isophotal radius, so you pick some surface brightness limit and measure the size of things above that limit. There's also a core radius where you fit a Gaussian or some other profile to these clumps. And so we found that to compare the high redshift and low redshift data, this core method was maybe more comparable because of the different surface brightness limits and all of these other problems. So the low redshift black points, we fit ourselves to the H2 region, H2 images from the SING survey. So we measured those in the same way that we measured the high redshift clumps, where we identified peaks in the H-alpha luminosity. And then from those peaks, we fit 2D Gaussians to the clumps themselves, allowing them not to be symmetrical and these sorts of things. And then for the giant H2 region data, we only used data from the literature, which was measured in a similar way, using this sort of core radius. So that was how we tried to be as consistent as possible in the size measurements. But again, it's data spanning many decades as well as many different instruments and telescopes. So that was sort of the best that we came up with to do it.
I have a comment for Jorge and a question for you. A comment regarding your question on the metallicity influence in these correlations. You're right, at high redshift it is difficult or it cannot be done, but at low redshift it has been done. Because in fact, the first correlation was obtained by Melnitz, Terlevich, Teles, and etc. And they used the most metal-proof world system they knew. So this was Eduardo Teles' work in here. This is much of these first work in this correlation were done with this sample. Then the H2 region or the giant H2 regions are more metallic, and they also follow. So at low set, maybe not the extremely metal-poor things, but different samples with different metallicities have been explored for this correlation. And I have a question, a simple question about migration. So what is the typical velocity of these clamps when they migrate? Because it happens to me that, again, looking to the local counterparts that we have in mind, if you have such a massive clamps forming stars moving in a medium, which is the disk of the galaxy, which even if it is very turbulent and and the sound velocity is higher, still this is a fixed velocity. So if you move a clamp at a velocity which a bit of the order of the sound speed that it probably would be, you are expected to find a tremendous bow shock forming, facing the movement. So to me, but I don't know, I have no idea what is the typical velocity which is expected for this migration. But if it is of the order of the sound velocity, to me, a good test to explore whether this is working or not is to look for bow shock structures near these clamps, which are supposed to be candidates to be moving to the center of the galaxy.
No, that's a really good point. I think if we can try to get the data deep enough to look for the bow shocks from maybe the wind signatures. I don't know off the top of my head what the typical velocity is expected for migration, but it should happen over a dynamical time, so it's pretty quickly.
It will be quick,
Yeah.
Yes. In principle, I would expect it to be quick enough to generate this structure that, in principle, you could see.
I've got comments rather than questions.
Okay.
In my group, we look at local galaxies in detail, and we look at star-forming regions. We look at H2 regions, basically. And in recent times, in the last year or so, we believe that we've detected two different regimes with two different scaling relations. One of these relates to H2 regions with luminosities lower than about 10 to the 38th, and the other higher. Without elaborating, it would be surprising if, when you go to high redshift, you are also not seeing two different scaling relations, if they're real in the local universe. The detection principle is that we can measure the mean electron densities in the regions, and we find that for regions lower than this, roughly 10 to the 38 or so, the electron densities are declining with radius. But above that, they're rising with radius. And this affects all the other scaling relations that you've mentioned. We find, for example, that there are two populations of H2 regions, two populations of molecular clouds also. We find this looking at using interacting galaxies as the triggers for the larger molecular clouds and the brighter H2 regions. I shouldn't say more, it's your talk, but there's a lot of things we can say about this. And I think it might be interesting that, to show you this, because it certainly reflects on what you've been saying.
It would be great to hear more about that. I think for high redshift to detect a change in slope, we'd need more regions.
Okay.
This is a comment about this discussion on the speed of the clamps with respect to the background galaxy. I think, well, I have in mind the simulations by Elmegreen published last year about BCDs and the migration of clamps in BCDs. And I think it takes like a giga-year for the clamps to make to the center. So this is very slow, I would say. So I doubt that you will see a... Yeah, but I guess that they rotate with the, surrounding stars and gas of the galaxy. They are not like going in the opposite direction or something like that. And so, I mean, you mentioned that it might happen that the velocities are high. I don't think so. I don't think so. I think that the velocities are fairly low to create things like shocks.
What about redshifts higher than 2.5? Has anything been done in other lines?
So two of the points that were quite offset were from a redshift almost 4.9 galaxy that was lensed. So it showed that two order of magnitude offset in star formation. But behind that, it would have to be lensed galaxies to really get at that question, and it's hard to know ahead of time a priori if they're clumpy disks. There's so much that goes into these lens studies, so nothing has been done yet.
Thanks.
Hi. How can you tell at high redshift the difference between a clumpy disk and a galaxy merger? I mean, the morphologies of some of these guys are completely wrecked.
Yeah. So we're using the velocity dispersion maps that we get from the IFU data, and even with those, it can be still quite difficult. Not everything looks like a perfect exponential disk. But there's various tests like kinematry, for example, where you can try to get statistically at the variations in the velocity maps and these sorts of things. So it's the best that we can do. But if you go back in 10 years and say, you know, we're 10% of the kinematic identifications wrong, probably. But it's what we can do at the moment.
And a couple of days back, there was a paper by Phil Hopkins on Astro-V8.
I saw that when I first arrived. I haven't read it yet.
You haven't read it? Okay.
No, it basically says that cold flows don't cause these higher dispersions.
Yeah. Okay.
It's something about this paper by Hopkins. Okay.
Yeah.
No, it's simply that the cold flows, I mean, in this paper, what he calls cold flows might not be what others call cold flows. These are very mild cold flows. So the accretion rate is like 10, so for a Milky Way galaxy is like 10 solar masses per year. I remember these things because I read it yesterday. So that's, and so this means that in order to create the disk, you need like 10 gigayears or so. Okay. And they say at the very end, that, I mean, if you have what other people call minor mergers, which are large cold flows, then, of course, things are different. Yes. So these are fairly mild cold flows.
If you look also at the observations, there is more gas in the high-redshift galaxies, more star formation. So you can just look at it empirically and say, yes, this does make sense that they're perhaps more turbulent.
Okay, I think, well, maybe you have another question? No. We can stop here, and you know now in the library we have a scientific coffee. You can discuss a bit more with Emily. Let's thank her again.